What's up, YouTube? Nakita ba mo algorithm na pang navigation, pang games? Pues, iba-ilailata mo kay Star Search algorithm.
Hello everyone, today we're doing a deep dive into the A-star algorithm, breaking down the math formula that drives it, analyzing its operational mechanics and time complexities, and assessing its real-world applications. So, a quick introduction. The A-star algorithm stands as the gold standard in graph traversal, bridging the gap between brute force search and pure heuristic estimation. Unlike its predecessors, A-star prioritizes the expansion of paths based on a calculated total cost, ensuring that computational resources are focused strictly on the most promising directions. By blending the exhaustive accuracy of Dijkstra's algorithm with the forward-looking intelligence of greedy best-first search, A-star maintains both completeness and optimality. This unique combination makes it indispensable for modern artificial intelligence, mapping applications, and autonomous systems. The mathematical foundation of the algorithm. The A-star algorithm follows a formula of f of n is equals to g of n plus h of n. The operational intelligence of A-star relies entirely on a single elegant cost function to evaluate every potential node in the search space. The component g of n represents the exact history of the path, calculating the precise cost incurred to travel from the starting point to the current node n. Conversely, h of n represents the future, serving as an estimated heuristic cost to bridge the gap between node n and the ultimate goal. By summing these values, the total evaluation f of n allows the algorithm to make mathematically sound decisions that balance where it has been, where it is going. So we move from the time complexity of the algorithm. The A-star algorithm has a best case time complexity of O of D. In the absolute best case scenario, the time complexity is linear relative to the depth of the solution. So how does this happen? This occurs when you have perfect heuristic, meaning h of n is equals to h star of n, where h star is the exact true cost from node n to the goal. With a perfect heuristic, the algorithm never expands a node that isn't on the optimal path. It walks straight from the start node to the goal node, evaluating exactly the nodes. Now, the algorithm has a worst case time complexity of O of b to the power of d. In the worst case scenario, the time complexity of A star is exponential. So this happens when the heuristic is highly inaccurate or completely uninformative. For example, if h of n is equals 0 for all nodes, A star degenerates into Dijkstra's algorithm, or breadth first search if edge weights are equal. The algorithm is forced to explore the entire search space in all directions before finding the goal.
Hello everyone, in my part, I'm going to discuss the rule of heuristics. The performance and accuracy of A-star search are directly tied to the design of the heuristic function, which must be tailored to the rules of the environment. For the algorithm, to guarantee the absolute shortest path, the heuristic must be admissible, meaning it can never overestimate the true cost to reach the goal.
Yes.
These are the common heuristics. 3 common heuristics: Manhattan distance, Euclidean distance, and diagonal distance. Manhattan distance is used for four-way movement: up, down, left, and right. Calculates the horizontal and the vertical distance. Euclidean distance is used when a movement at any angle is allowed. It calculates the straight line distance like a crow flies. The diagonal distance is used when a two-way movement is allowed.
Assessment of the A-star algorithm. This report presents the result of the algorithm assessment conducted on the A-star search algorithm as implemented in A-star Pathfinder Java. The pathfinding core of the desktop tower defense system developed for IT-221 data structures and algorithm. The assessment evaluates the algorithm's time complexity across multiple realistic gameplay scenarios, measures execution time against a BFS baseline, analyzes node exploration efficiency, and verifies compatibility with the game's 60 FPS real-time constraint. All results reported here are empirical, collected from a controlled benchmark executed directly against the project's source code on a 25 by 17 grid, total of 425 cells. The results: A. The nodes explored. Nodes explored is the primary measure of algorithm efficiency. Every node explored incurs a priority queue operation, or ON log n, and a cost comparison, so fewer nodes directly translates to faster execution and a lower CPU usage. Scenario: open grid or no towers, 25 A-star nodes and 333 VFS node. So reduction is 93%. Light load: 30 towers, 50 A-star nodes, 369 BFS nodes, and 86% reduction. Medium load: 80 towers, 128 A-star nodes, and 340 BFS nodes with a 62% reduction. Maze: 3 vertical walls, 193 A-star nodes, 298 BFS nodes, and 35% reduction. Dense: 130 obstacles, 69 A-star nodes, 259 BFS nodes with a 73% reduction. Hard mode pair 1, 0 and 4, and 24 and 4. 27 A-star nodes, 321 BFS nodes with a 92% reduction. Hard mode pair 2, 12 and 0, 12 and 16. 19 A-star nodes, 278 BFS nodes with a 93% reduction. A-star consistently explore fewer nodes than BFS across all scenarios. The most dramatic reduction occurs on an open or lightly blocked grids where the Manhattan heuristic can guide A-star in a near straight line from spawn to exit. The open grid result is particularly striking. A-star evaluates only 25 of the 425 cells, or 5.9%, to find the optimal path. while BFS evaluates 337 or 79.3% before reaching the same goal. The smallest reduction, 35%, occurs in the maze scenario where 3 vertical walls force a star to explore more cells to route around barriers. Even so, a star still evaluates 35% fewer more cells than BFS. The hard mode pair results confirm that a star scales cleanly to multiple simultaneous path queries with no degradation in the node efficiency. B. Execution time. Execution time was measured in microseconds per call, average over 2,000 runs after GVM warm-up. Scenario: open grid, no towers. A start time, 36.69 microseconds. BFS time, 59.22 microseconds. Speed up 1.61 times. Light load, 30 towers. A start time, 33.05 microseconds. BFS time, 19.47 microseconds. Speed up is 0.59x. Medium load, 80 towers, 45.99 microseconds ang A-star. BFS time, 10.13 microseconds with a speed up of 0.22. Maze, 3 vertical walls. A-star time, 26.43 microseconds. BFS time, 8.65 microseconds. Speed up 0.33 times. Dense or 130 obstacles. A start time 11.56 microseconds. BFS time 7.22 microseconds. Speed up 0.63x. Hard mode pair 0 and 4 and 24 and 4. A start time 7.99 microseconds. BFS time 8.26 microseconds. Speed up 1.03x. Hard mode pair 2 12 and 0, 12 and 16. A start time 5.69 microseconds. BFS time 7.20 microseconds. Speed up 1.27x. Is spot survivable call? A start time 9.14 microseconds. BFS time not applicable. NA. 60 FPS frame budget analysis. A real-time game running at 60 frames per second allocates 16.67 milliseconds per frame for all computation. Pathfinding must be complete within a small fraction of its budget to avoid visible frame drops. Scenario: open grid, no towers, with a 0.0367 ms and a percent of frame of 220% and a 454 calls or frame. Light load, 30 towers, with a 0.0331 ms and a 0.198% of frame and a 504 calls or frame. Medium load, 80 towers, with a 0.0460 ms and a 0.276% of frame and 362 calls or frame. Maze, 3 vertical walls, with a time of 0.0264 ms and 0.158% of frame and 630 calls or frame. Dense, 130 obstacles with a 0.0116 ms and a 0.069% of frame and 1442 calls frame. Hard mode pair 1, 0 and 4 and 24 and 4 with a time of 0.0080 ms and a percent of frame of 0.048% and 2085 calls or frame. Hard mode pair 2, 0 and 12 and 0 and 12 and 16 with a 0.0057 ms and 0.034% of frame and 2,928 calls or frame. Is spot survivable call with a time of 0.0091 ms and 0.055% of frame and 1,823 calls or frame. Even the slowest scenario, medium load at 0.046 ms, consumes only 0.276% of the frame budget. The game loop invokes find fat at most twice per frame event, once per spawn exit pair in hard mode, and is spot survivable only when the player attempts a tower placement. In practice, pathfinding accounts for less than 0.01% of total frame computation, leaving the frame budget entirely free for rendering, physics, and game logic. So, here are the summary of our findings. Finding 1. Node efficiency. A-star explores 35 to 93% fewer nodes than BFS across all scenarios. On open grids, it evaluates under 6% of all 425 cells. Finding 2. Time performance. A-star completes in 5.69 to 45.99 microseconds per call. All scenarios are well under 0.05 ms and making the algorithm fully real-time compatible. Finding 3. Priority queue overhead. BFS is faster in wall clock time on dense and maze scenarios due to O1 queue operations versus O login for A-star's priority queue. This is a grid size effect and does not affect real-time viability. Finding 4. Frame budget. Worst case, A-star consumes 0.276% of the 16.67 ms frame budget. The game can call find fat 362 to 2,928 times per frame before approaching the budget limit. Finding 5. Placement validation. Is spot survivable costs 9.410 microseconds per call, imperceptible to the player, and safe to invoke on every tower placement attempt.
So, the conclusion. The A-star search algorithm with Manhattan distance heuristic is the correct and well-justified choice for the tower defense pathfinding system. It is complete, optimal, and real-time safe across all tested gameplay configurations. the algorithm's dual role as both a pathfinder and a placement validator demonstrates its centrality to the system's core functionality, not merely as a peripheral feature, but as the architectural foundation that makes the game mechanically sound and strategically consistent. The empirical assessment confirms that A-star operates comfortably within the 60 FPS frame constraint, exploring a fraction of the nodes that an uninformed algorithm would require while guaranteeing that every path returned is the shortest possible route from spawn to exit.
So, before we're going to start, let's talk about the formula. F is a total estimated cost of the optimal path passing through node. And G is the exact accumulated path cost from the starting node to the current node. And H, the heuristic estimated cost from current node to the final goal. So, we're going to start from S to Z. On the formula, here is the G and here is the H. So, let's start. Let's try going to B. S to B. So, S to B path costs 4 and B costs 8. 4 plus 8 is equal to 12 points. How about the A route? S to A. S to A path costs 3 points plus 7 on A. 3 plus 7 is equal to 10. So, A is lesser than B. So, we're going to take the A route since it is much lesser than B. So, A route has 2 paths, E and C. So, since G is the exact accumulated path cost from starting node to the current node, we're going to add the G's we've been passed through. Let's start with A to E path. 3 plus 1 is equals to 4 plus 5 is equal to 8. This costs 8 points. How about here? A to C path. A to C path costs 6 points. 3 plus 3 equals 6. Plus 6 on the C equals 12. So, here is 8 points and here is 12 points. So, E is less than C. So, we're going to take that route. So, E has 2 paths, I and G. E and I has a path of 7 points. 3 plus 1 plus 3 is equal to 7. And plus I, 3 is equals to 10. 10 points. 3 plus 1 plus 3 equals to 7. Plus 3 is equal to 10. Now, this route takes 10 points. How about this route? E to G. 3 plus 1 plus 4 is equal to 8 plus G 5. 8 plus 5 is equal to 13 points. So this one takes 13 points. So is G lesser than I? No. So we're going to take I route. So on I route, it only has one route, I to Z. So G is equal to 3 is equal to 9. 3 plus 1 plus 3 plus 2 equals 9. Since Z doesn't have a point, we're going to copy the G, put it in the H. So Z has a value of 9 points. 9, 3 plus 1 plus 3 plus 2 equals 9, plus 9 is equal to 18 points. So going to I to Z costs 18 points. Now you've learned how a star search algorithm works. Video, I'm going to showcase our system that is called Medieval Fantasy Tower Defense Game. Using a star search algorithm, it has a 3 difficulty which is called easy, medium, and hard. Let's try hard. Then you have to defend your base, which is this one and this one. So the enemy spawns here, these two. Also, this is your base. This is the things you have to protect, so watch out for it. So let's try defending it again. Let's fast forward it, since so you also cannot block the enemy's path, since it needs to go on a path. So sell here, then I mean sell banana, then so sell archers, then you cannot put here, then put here. You can also upgrade your towers. It has 4 types of towers: archer, knights, and mage and marksman. The enemy leading creep has also a path meter. The path meter has a formula of Fn equals to Gn plus Hn. This path meter calculates how many steps does the leading creeps needs to go on the top on their goal. So yeah, now it is completed. That's it for our system called Medieval Fantasy Tower Defense Game. Bye bye.